Next one is the hydroboration oxidation of an alkene. The acid catalyzed hydration added an H2O equivalent across a double bond, but the OH ended up on the most substituted carbon. This one, we're going to end up on the least substituted carbon. So if we start off with this, this is our end goal here. This will still depend on the stability of the carbocation though. So remember that BH3 is a Lewis acid, so it likes to accept electrons. That being said, here's your BH3, it's your electrophile, your Lewis acid, has a little empty p orbital there. This is your nucleophile, it's going to pop up in there. You're going to get a different intermediate than normal. We're going to have the BH3 bond here, but this other hydrogen is going to be bound like that. So it's going to be your intermediate. Why? Good question. It's not any different than just saying BH3 with a minus and a plus here. I already messed up. That's not the most stable carbocation. This was a learning example for the both of us. So let's try this again. Put the BH3 over here, the plus charge over here. The hydrogen is going to act as a hydride in this case, just as you normally see BH3 or BH4, I guess. So this hydrogen would pop down here, but the backwards example. So maybe draw this then. There you go. So these two electrons are going to come down here. That's going to give you your proton there and BH2 here. Now, here is where the magic happens. We were not asked to learn the mechanism for this, so we're just going to write H2O2 peroxide and NaOH, I guess aqueous or with water, and that's going to turn any borane into a OH group. I lost a carbon at some point. Happens to all of us. So we're not asked to know the mechanism for how the borane turns into the hydroxide. We also learned other boron-containing compounds. We did that 9BBN thing. That's just a bit bulkier, so it's more stereoselective. But in terms of this mechanism, we're still going to have the alkene nucleophile. We're still going to have an electrophile, the BH3. We still depend on the most stable carbocation, which is this one, not this one. Except instead of the OH or your nucleophile coming down here, that's an H minus that comes down. So in the other reactions, we have an H plus as the first step. We're going to have an H minus as the second step, which is what allows us to get the hydroxide on the least substituted carbon. So when you guys are doing your retrosynthesis and you see an alcohol, you could think of reducing a carbonyl if you want, but you could also go from an alkene to an alcohol via the most or least substituted carbon based on the last two mechanisms that we've done.